We are going to start now lecture 3 of chapter 1 class 10th mathematics real numbers. So in this lecture we will talk about the rational numbers and irrational numbers. Some properties we have already studied in our previous classes. So we review some basic definitions. So first thing we have, it is natural numbers. So numbers which are used for the counting purpose, we are saying 1, 2, 3, 4, all these numbers, these are the natural numbers. Then we add 0 to it. This collection we are saying 0, 1, 2, 3, 4, so on, these are the whole numbers. Then we add to this collection the negative numbers, we are saying -1, -2, -3 and so on. Then 0, 1, 2, 3 and so on. These are the integers. So the next we have it is rational numbers. So rational numbers, the definition was the numbers in the form of p by q, where q is not equal to 0, and p and q, they both are integers. They are represented with z. So these are called the rational numbers. These are represented with q. Then we have studied the rational numbers have the decimal form. So in decimal form we are saying that decimal form can have two basic forms. One is the terminating decimals and one is non-terminating decimals. These non-terminating decimals can further have two classifications. It is non-terminating and repeating, and non-terminating and non-repeating. So we have studied in our previous class that when we are talking about the rational numbers, rational number means their decimal representation is either they are terminating or they are non-terminating and repeating. So both these, the numbers which are in these two categories, they form the rational numbers, and the numbers which have decimal representation, that is non-terminating and non-repeating, they are the irrational numbers. Next is to test whether a given rational number is a terminating or a repeating decimal. So we are saying let x be the rational number whose simplest form is p by q, where p and q are integers and q is not equal to 0. Then x is terminating decimal only if q is of the form 2 raised to the power m into 5 raised to the power n for some non-negative integers m and n. And the decimal form that we will have, it will be non-terminating repeating form if q is not of the form 2 raised to the power m into 5 raised to the power n. So to clarify this, what we mean to say is that any number that is given to us, say the number given to us, it is 3 by 20. Then we are talking about this is of the form p by q. We know it is the rational number. So it may have two form, either the terminating, its decimal representation as maybe terminating decimal, or it may be non-terminating repeating. So in place of solving this, we look at this value q over here. We are saying this q is 20, and if we do the prime factorization, then we will have the answer is 2 raised to the power 2 into 5 raised to the power 1. So we are saying that the denominator of this number has the form 2 raised to the power m into 5 raised to the power n. We are saying m is equal to 2 and n is equal to 1. So what we get is that this number will have a terminating decimal representation. So we need not to solve this. We can just, by looking the denominator and its prime factorization, we can tell whether the number will be terminating or non-terminating decimals. So next we will see certain examples related to this, and it will be more clear to you that what this result tells us. So next is without actual division, show that the following rational number is a terminating decimal and express each in decimal form. So the first number that is given to us, it is 31 over 2 raised to the power 2 into 5 raised to the power 3. So if we look at this number, the denominator is of the form 2 raised to the power m into 5 raised to the power n. We are talking about this number over here, 2 raised to the power 2 into 5 raised to the power 3, it is of this form. So the result says that it has terminating decimal representation. Now if we have to calculate its value, we are saying we are having 31 over 2 raised to the power 2 into 5 raised to the power 3. We multiply and divide this term with 2, and the answer we get, it is 62 over 2 raised to the power 3 into 5 raised to the power 3. This value becomes 2 into 5 raised to the power 3, and this becomes 10 raised to the power 3. We are talking about this denominator part. 10 raised to the power 3 means this becomes 1000, and the answer that we will get over here, that is equal to 0.062. So we see that it has a terminating decimal representation. Next is 33 over 50. Next part is 33 over 50. So if we look at the denominator over here, denominator is 50. That is equal to 2 into 5 square. So we get that the value of m and n over here, it is 1 and 2, and it is of the form 2 raised to the power m into 5 raised to the power n. Again, if we have to write this number in the decimal form, we are saying it is 33 by 50. We multiply and divide it with 2. Why? This power is 1. To make it equal to this power, we have multiplied it with 2. So this becomes 66 by 100. So answer we will get, it is 0.66. Next is the number given is 41 by 1000. So we are talking about the denominator over here. So denominator is 1000. It means I am talking about, it is 10 raised to the power 3. That is 2 into 5 raised to the power 3. That is 2 raised to the power 3 into 5 raised to the power 3. So again it is of the form 2 raised to the power m into 5 raised to the power n. So value of m we get, it is 3, and value of n we get, it is 3, and the decimal representation of this number will be 0.041. Now next is 17 by 625. You can write it like 17 by 5 raised to the power 4. 625 is 25 into 25, and this is 5 raised to the power 4. So we are saying that this number is of the form 2 raised to the power m into 5 raised to the power n, where m is equal to 0 and n is equal to 4. So it means this number will have a terminating decimal representation, and when we have to calculate the value of that decimal, the answer will be 17 by 5 raised to the power 4 into 2 raised to the power 4 into 2 raised to the power 4. So it becomes 17 into 16 over 10 raised to the power 4. So it is 272 over 10,000. So it is 0.0272. So this is our answer over here, that the decimal representation of this number, it is 0.0272, and it is terminating decimal representation. And this thing is also clear from the fact that the denominator is of the form 2 raised to the power m into 5 raised to the power n. Now next we are talking about, we have to find whether these numbers, we have to prove that they have non-terminating repeating decimal representations. So first number that is given to us is 121 over 2 raised to the power 3 into 3 raised to the power 2 into 7 raised to the power 5. So first of all, we have to check whether this is in the simplest form or not. So we see that 2 is not a factor of 121, 3 is not a factor of 121, and 7 is not a factor of 121. It means this number is already in the simplest form. Now if we look at the denominator of this number, the denominator of this number is not of the form 2 raised to the power m into 5 raised to the power n, because there are factors 3 and 7 also. So it means that this number will not have the terminating decimal representation, it will have non-terminating repeating decimal representation. Repeating because it is the rational number, so it will be repeating, it cannot be non-repeating. So this number will have non-terminating and repeating decimal representation. Next number that is given to us is 17 by 90. So we are talking about the number 17 by 90. So if we factorize 90, we see that its prime factors are 2, 3 raised to power 2 into 5. If we are talking about the prime factorization of 90, so it becomes 2 into 3 raised to power 2 into 5, and none of these values is the factor of 17. That is, we are saying 17 is not divisible by 2, 3 or 5. So it means this number is already in the simplest form. Now the denominator we are talking about, it is 2 over here, 5 over here, but this term 3 raised to the power 2 is also there. So we are saying that the denominator is not of the form 2 raised to the power m into 5 raised to the power n, but there is another number that is into 3 raised to the power say k over, so it is of this form. So it means that the decimal representation of this number is non-terminating repeating decimal. The decimal representation is non-terminating and repeating decimal. Next is given number is 53 by 343, and 343 is, you can write it is 53 over 7 raised to the power 3. Now again we can see that 7 is not factor of 753. So it means this number is in the simplest form. Now look at the denominator. It is not of the form 2 raised to the power n into 2 raised to the power m into 5 raised to the power n. So it means that this number will have a non-terminating repeating decimal representation. Next is the number 66 by 180. So if we look at this number, we see that the HCF of both these, we are talking about the HCF of 66 and 180. If we calculate the HCF of these two numbers, it is 6. We have to find the factors of these two numbers, and we will see that the HCF of these numbers is 6. So it means we can divide both these numbers with 6 to find the simplest form. So when we divide these two numbers with 6, we get the simplest form is 11 over 30. Now if we factorize this 30, we see that it is 2 into 3 into 5. Again 3 is there. It means that this number, the decimal representation of this number will be non-terminating and repeating decimal. It means the decimal representation of this number will be non-terminating and repeating decimal. It is important to note over here that we have to simplify the number to find the answers. So this thing will be more clear if I suppose I am talking about the number say 33 over 60. So if we look at the denominator over here, if we look at this denominator over here, its factors, if I factorize 60, what we see is it is 3 into 20. Now we are talking about this 20 over here. So if we factorize this 20, we get it is 2 raised to power 2 into 5. So what we can, if suppose I am not simplifying this and I am just writing that 60 has factor 3 into 2 raised to power 5 into 5, what we get is it is 3 over here in the denominator. So we can say that it has the terminating decimal representation. It has a non-terminating and repeating decimal representation, but what we see is that it is 33 over here and this 3 is over here. and it is a factor over here, so we can simplify these terms and it will become 11. So we are saying the simplified form of this term is 11 by 20. And when we are talking about 11 by 20, 11 by 20 means the denominator is 2 raised to power 2 into 5. It means it will have a terminating decimal representation. So if we are not simplifying it, our answer is this way of calculating it is incorrect. So first of all, we have to simplify it and bring it to the simplest form, bring the fraction to the simplest form. Only after that we will look at the denominator and we will talk about this form 2 raised to the power m into 5 raised to the power n. Otherwise our answers may become incorrect. Now next we have to find that this number is given to us 43 by 2 raised to power 4 into 5 raised to power 3, and we have to find after how many decimal places the decimal representation will terminate. So we are talking about the number 43 by 2 raised to the power 4 into 5 raised to the power 3. We multiply and divide this number with 5 and we get it is 215 by 10 raised to the power 4. So it is 215 by 10,000. The answer is 0.0215. So we are saying that it will terminate after 4 places of decimal. This next question, this is based upon we have to express the rational numbers in the simplest form. So these kind of questions we have already studied in our previous class. In class 9th we have studied this. So these are just the review problems that we are repeating over here. So first number we have it is 0.6 bar. So this 6 bar means that 6 is repeating over here. So how we used to calculate these values? We are saying suppose x is equal to 0.666 so on. It is bar on only just one number, one digit is there. So we are saying 10x is equal to 6.666 and so on. So we have obtained two equations over here. One is this and second is x is equal to 0.666 and so on. So if we subtract these two equations, we get 9x is equal to 9x is equal to 6. So this implies x is equal to 6 by 9, that is equal to 2 by 3. Next is x is equal to 1.8 bar. Again bar is on a single digit. So what we are going to do is we are going to multiply it with 10. So we are saying 10x is equal to this number. When we are writing, it is basically 1.888 and so on. So this will become 18.888 and so on. Next we are saying x is equal to 1.888 and so on. So if we subtract these equations, we get 9x is equal to 17. So we get x is equal to 17 by 9 and that is equal to 1 whole 8 by 9. Now next we have x is equal to 0.16 bar, that is equal to 0.1666 and so on. So now the repeated digit, these are the repeated digits. So first of all what we are going to do is we are going to do 10x is equal to 1.666 and so on. We have converted this question to this form. This is just like the previous question now. So what we have to do is we are multiplying again it with 10. So we are saying 100x is equal to 116.666 and so on. 10x is equal to 1.666 and so on. When we subtract these two equations, we get it is 90x is equal to 15. It means x is equal to 15 by 90, that is equal to 1 by 6. So in this question it is important to see over here that this 1 was not having the bar over here. So we have converted this to the form 10x is equal to 1.6666, and then we have solved this problem. Next is, suppose we are saying x is equal to 0.323232 and so on. So how many digits are repeating over here? These are two digits that are repeating. So what we are going to do, we are going to write 100x is equal to 32.323232 and so on. Again, when we subtract this equation from x is equal to 0.3232 and so on, we get the answer is 99x is equal to 32. So this implies us x is equal to 32 by 99. Now next we are having x is equal to 0.2545454 and so on. So the repeated digits, these are the repeated digits over here, 5454. We are having this 2. So first of all we have to remove this 2 from here, from this decimal. So what we are going to do, we are going to write 10x is equal to 2.545454 and so on. Now we are going to solve this problem and we have to multiply it with 100. So we are saying 10 is already there, we are multiplying it with 100 and we get it is 254.5454 and so on. And when we subtract the equation, we get the answer is 990x is equal to 252. This implies us x is 252 by 990. It means it is, when you simplify these values, we are dividing it with 2 first, then it is 126 by 495, and then when we simplify these values, you will get the answer is 14 by 55. This is your final answer that you will get after simplifying these values. Now next we are saying we have to show that the following numbers are rational, and what you can say about the prime factors of their denominators. So if we look at this number over here, we are saying that this number is, the decimal representation of this number is of the form that it is terminating decimal representation, and we know that the numbers having terminating decimal representation, they are rational numbers. So if it has terminating decimal representation, it means its denominator will be of the form 2 raised to the power m into 5 raised to the power n. What this thing means, that will, its denominator will have the prime factors as 2, multiples of 2 or multiples of 5. The denominator will have these prime factors. Next is 32.123456789 bar. So we are saying that what kind of number is this? The decimal representation is, it is non-terminating and repeating decimal. So we are saying it is a rational number and its denominator will have some factor, some prime factor other than 2 and 5. If we look at the decimal representation of the denominator of this prime number, this rational number, then it will have some factor other than 2 and 5. Next is, we have to decide whether this number is rational or not. This number is given to us. So what we see over here, if you look at this value, it is 1 2, then it is 1 0 over here, then it is again 1 2, then there are 2 zeros over here, then it is again 1 2. Talking about these values over here, that this 1 2 1 2 1 2 1 2 is there. But the problem over here is that it is after 1 0, this is after 2 zeros, then it is after 3 zeros. So we cannot say that the number is repeating. So what kind of decimal representation is this? This representation, we are saying it is non-terminating. First thing, it is not terminating, and it is non-repeating decimal representation. the number, they are not repeating after certain steps. We cannot put bar. Suppose I am writing 0.12012 bar. What this 12 bar will mean? It means it is 121212. But this is not the number given over here, because the number of zeros that we will have, if suppose I am writing 0.12012 bar, it means it is 012 but these numbers, we are saying these zeros, they are increasing as we are moving forward. So these kind of representation, these are non-terminating and non-repeating decimal representation. So we are saying that this number is an irrational number. It is not a rational number. So the next definition we have, it is irrational number. So numbers which when expressed in decimal form are expressible as non-terminating and non-repeating decimals. Here is decimal representation we are talking about. It is non-terminating and non-repeating decimals are there. These kind of numbers, these are called the irrational numbers. These are called the irrational numbers. Next, some examples are given over here. So in the first, this example, we are talking about this number we are talking about. So what kind of number is this? We are saying it is 0.1. Then 1 0 is there. Then again it is 1. Then 2 zeros are there. Then again it is 1. Then 3 zeros are there. Then again it is 1, and so on. So we are saying that these blocks, if we look at this block, we cannot find something that is repeating over here, some blocks that are repeating over here. So we are saying that this number, it has non-terminating and non-repeating decimal representation. Similarly, in this second number, again this third number, again with a similar reasoning we are talking about. All these numbers, these are irrational numbers. Next number that is given to us, it is 0.12. Then it is 112. Then it is 1112. Then it is 1112. So on. Again, the blocks, they are not repeating over here. All these numbers, these are different numbers. All these blocks, they are not repeating, they are different. So we are saying that what kind of representation is this? This is non-terminating and non-repeating representation. So it means both these numbers, these are irrational numbers. Similarly, if we are having any positive integer m which is not a perfect square, then what we have is square root m is irrational. So we are talking about these numbers over here, that square root of 2, square root of 3, square root of 5, square root of 6, square root of 7, 8, 10, 11, all these numbers, these are irrational numbers. Similarly, cube root of 2, cube root of 3, cube root of 5, cube root of 6, all these are irrational. Suppose I am talking about square root of 4. So 4 is a perfect square, the answer I will get it is 2. So it will be a rational number. Suppose I am talking about cube root of 8. The answer is 2. If I am talking about cube root of 27, the answer is 3. So these numbers, we are not saying that all the square roots are irrational. For square roots, we are saying if m is a positive integer which is not a perfect square, then square root m is irrational. Similarly, if m is a positive integer which is not a perfect cube, then we are saying that cube root of m is irrational. Next, we have numbers like pi. It is irrational. And in our previous class also we have discussed about that 22 by 7 is rational. This is just an approximation of pi. This is not the exact value of pi because it is a rational number, whereas pi is an irrational number. So this is just an approximation of pi, that is up to certain digits of decimal, their values are same. After some point, the decimal representation of 22 by 7 will start repeating, but the decimal representation of pi will never repeat. Now next is this theorem that in which we have to prove that let p be a prime number and a be a positive integer. If p divides a square, then show that p divides a. If suppose I am talking about, if we give some example over here, if suppose I am saying 3 is a prime number, this is not the proof I am talking about, this is just an example of this. I am telling you that what we are going to prove or what we want to prove is, and we are saying a be a positive integer, and it is such that if p divides a square, suppose I am saying the value of a, it is 6, this is a, this is the number p, so a square is 36. So we are saying 3 divides 36, then 3 divides 6 also. This is what our theorem is saying. So we are saying how we are going to prove this. It is let p be a prime number and a be a positive integer such that p divides a square. Then we know that every positive integer can be expressed as product of primes. So we are saying that the number a that is given to us, suppose its prime representation, it is p1 into prime factorization we are talking about, is up to pn, where these p1, p2, p3, so on up to pn, these are primes, and it is not necessary that all these are distinct. Suppose I am talking about the prime factorization of 20, then its value is 2 into 2 into 5. This is a prime factorization, but both these numbers, these are same. So we are saying this is p1, this is p2, this is p3. So this is what we are talking about, that is the number a we have, that is any positive integer we are talking about. It will have a prime representation in this form. Then we are saying if we square this number, we get a square is equal to p1 square into p2 square, so on up to pn square. Now what is given to us is that p divides a square. It means p is a prime factor of a square. If p divides a square, and these are the prime factors over here, it means that p is a prime factor of a square. What it means? These are the prime factors we have. It means p is one of p1, p2, so on up to pn. And if p is one of these values, and we have a is equal to p1 into p2 into p3, so on up to pn. So what we see from this is that this p will divide a. So we are saying this p will divide a. So we get our final answer that p divides a square. This is symbol for implies that p divides a. So what is the basis of this proof? We are saying if p divides a square, it means that p is the factor of a square, that is p is one of these numbers. If p is one of these numbers, then these numbers are also the factor of a, and hence we are able to prove this theorem. Now the first result that we have to prove is that square root 2 is irrational. So we are saying, suppose we consider that square root 2 is a rational number. We have to prove that square root 2 is irrational. So we are proving this thing with the method of contradiction. Contradiction means we suppose that square root 2 is a rational number, and its simplest form is square root 2, we can write it is a by b. If it is rational number, then it is of some form a by b, where a and b, HCF of a and b, it is 1. This is the simplest form. So it means HCF of a and b, it is 1. A and b, we are saying these are some integers, and third thing we have, it is b is not equal to 0 because it is a rational number. So we are saying these are the properties of the rational number that we will have if it is of the form a by b. Now if we square both side of this equation we get 2 is equal to a square by b square. This gives us 2b square is equal to a square. Now 2b square is equal to a square. What this thing means? That 2 divides a square. Why we are saying so? Because a square is equal to 2 times a b square. It means whatever the value of b is, suppose it is b square is 7, then value of a square is 2 times 7. If the value of b is 10, then the value of a square is 2 times 10. So it is always a multiple of 2. It means 2 divides a square. Now from our previous result we know that if a number p divides a square, it means p divides a also. This is from our previous theorem that we have proved. So what we get is that 2 divides a. So if 2 divides a, what this thing means is we can find a number c such that a is equal to 2 times c. You can also see this result as the Euclid's division algorithm. So we are saying if suppose a number a is given to us and we are talking about its divisibility with 2, then we are saying that we can find a number c and r such that a is equal to 2c plus r. Now we know that it is exactly divisible. So the value of r we get it is 0. So it means a is equal to 2 times c. So there exists a number c. C is just like the quotient over there. Over here we are writing it is c. So we are saying there exists a number c such that a is equal to 2 times c. So if we put this value in the equation, this one, that is 2b square is equal to a square, we put this value over here in this equation of. So what we get is 2b square is equal to 2c square, that is equal to 4c square. This gives us b square is equal to 2 times c square. Again with the similar reasoning we are saying if b square is equal to 2 times c square, it means 2 divides b. We are talking about this reasoning over here, that why 2 divides a we have seen over here. Similarly we are saying 2 divides b. So what we get is we are having two things now, 2 divides a, and second thing we have is 2 divides b. It means 2 is common factor of both a and b. And if 2 is the common factor of both a and b, what we have considered over here? We have considered that HCF of AB is 1. But from these two results I am talking about, we are saying that 2 is the common factor a and b. So it means this thing cannot happen, this thing will become false. So, and this thing cannot be false because this is the definition of the rational numbers. It means whatever we have supposed over here, this thing, that root 2 is rational, whatever we have supposed over here, it is false. So this thing is mentioned over here. We are saying 2 is a common factor of a and b. But this contradicts the fact that a and b have no common factor other than 1. We are talking about this thing over here, that HCF of a and b is 1. So we are saying the contradiction arises by assuming that root 2 is rational. So if we are saying that root 2 is rational, then a contradiction will come. It means we have root 2 is irrational. Root 2 must be irrational. Next we have to prove that root 5 is irrational. So again we are assuming that let root 5 be a rational number. Then we can write it in the form a by b, where a and b are integers having no common factors other than 1 and b is equal to 0. It means HCF of A and B is equal to 1. So what we have is root 5 is equal to A by B. If we square these terms, we get 5 is equal to A square by B square. This means A square is equal to 5 times B square. This thing gives us that 5 divides A square. From our theorem, we know that if P divides A square, then P divides A. If P divides A, it means there exists a C such that A is equal to 5 times C. If we substitute this value in this equation, we get it is 5C square is equal to 5B square. This gives us 5C square is equal to B square. This gives us 5 divides B square. This implies 5 divides B. Now we have two things, 5 divides A, 5 divides B. It means common factor of A and B. We are saying it is 5. The common factor of A and B, it is 5. And this is a contradiction to the fact that HCF of A and B is 1. It means whatever we have supposed, that is root 5 is rational, is wrong. That is root 5 is not a rational number, and if it is not a rational number, it means square root 5 is an irrational number, because this is the contradiction that is arising over here because of our supposition that root 5 is rational. Next is the general proof we are talking about, that if P is a prime number, then we have to prove that root P is irrational. So again, same procedure is there. We are saying P is a prime number, and if possible, we are supposing that root P is rational. If it is rational, it means we can write root P is equal to m by n, where m and n are integers having no common factor other than 1. It means, what does this thing means? HCF of m and n is equal to 1. Now root P we are writing equal to m by n. If we square these terms, we get P is equal to m square by n square. So this gives us m square is equal to P times n square. Now what this thing means? It means that P divides m square. We know that if P divides m square, then P divides m. If P divides m, then there exists a C. This is symbol for there exists a C. We are saying such that m is equal to P C. Now if we substitute this value in this equation, we get it is P C square is equal to P N square. It means P square C square is equal to P N square. So this means P C square is equal to N square. So this thing implies that P divides N square, and this implies that P divides N. So we are having two results over here. One is P divides M, and second we are saying P divides N. So it means that P is the common factor of M and N, and this is the contradiction to the fact that HCF of M and N is 1. That is the highest common factor of M and N, it is 1. It means the contradiction arises by assuming that root P is rational. It means that the assumption that we have made that root P is rational, it is not possible. So we get the result that root p is an irrational number. Now next is, if a is rational and square root b is irrational, prove that a plus square root b is irrational. Now to prove this result, we recall the result that we have studied in our previous class, that difference of rational numbers is rational numbers. So suppose we are saying that a plus square root b is rational. We have a is rational. So if we subtract both these, we are getting root b is rational. Because of this result we are talking about, that if two numbers that are rational, we are saying this number is rational, we are saying a is rational, when we are subtracting these two rational numbers, the answer must be a rational number, but it is given that root b is irrational. This contradicts the fact that root b is irrational. It means the supposition that we have made over here, that a plus root b is rational, this is, we have supposed, it means this supposition is wrong. We cannot suppose this thing. It means what we have is that a plus root b is irrational. It must be an irrational number. Now the next result we have, if a is a non-zero rational and root b is irrational, then we have to show that a root b is irrational. Now suppose we are saying, if possible, a root b be a rational number. If a square root b is a rational number, then it means we can write it in the form p by q, where p and q, these are non-zero integers. We are saying q is not equal to 0, and this HCF of p and q, that is equal to 1, that is, they have no common factor other than 1. So it means we can write a root b, that this number we are talking about, that is equal to p by q, then we can write root b is equal to p by q times a. Now we are saying these all numbers, this q, it is a rational number, it is an integer we are saying, so it is rational. This a, we are saying it is a rational number. It means this denominator that we have over here, this denominator we have over here, this is a rational number, and a is not equal to 0. This is given to us that a is not equal to 0, that is why we are dividing it over here. So what we see is that the denominator, this whole denominator over here, it is a rational number. So what we are saying is that root b is equal to p by q times a, and this thing means that if we can write this root b, this will become a rational number. This number is a rational number, and what this thing implies is that root b is rational, but it is given to us that root b is irrational. So this creates a contradiction over here. So we are saying, if we consider that this number is of the form p by q, then root b will be of the form p by q times a. It means root b will become a rational number, and this is the contradiction to the fact that is given to us that root b is irrational. It means the supposition that we have made over here, this is not possible. So we are saying root b, the contradiction arises by assuming that a root b is rational. It means a root b is irrational. Now next is, show that 2 plus root 3 is an irrational number. So we are saying, suppose we are talking about this number is rational. This is we have supposed. Then we are saying 2 is rational. If we subtract these two equations, we get root 3 is rational, and this thing is not correct. So our supposition that 2 plus root 3 is rational is incorrect. It means it is an irrational number. Another way to solve this is, suppose we are saying that 2 plus root 3 is rational, then it is of the form p by q, where p and q are integers and q is not equal to 0, and HCF of p and q it is 1. So we get root 3 is equal to p by q minus 2. So on simplifying this, we get it is p minus 2q by q. This is an integer. This is an integer. Denominator is not equal to 0. It means root 3 is equal to, suppose I am writing it as a. So it is of the form a by q. Q is not equal to 0. A and q both are integer. It means this implies that root 3 is rational and this thing is not true. Root 3 is rational is not true, it is incorrect. So it means 2 plus root 3 is irrational. So you can use either of these two methods. You can use this method or you can use this method to prove this result. Next is show that 2 root 3 is irrational. So suppose we are saying that 2 root 3 is rational. So it means there exists a and b such that 2 root 3 is equal to a by b. B is not equal to 0. HCF of a and b it is 1. It is also written over here that they are co-prime. Co-prime means that HCF of a and b is equal to 1. So what we get from this is that root 3 is equal to a by 2b. This thing means that, this thing implies that root 3 is rational, and we know that this thing is not correct. It means our supposition that this number is rational is wrong. It means 2 root 3 is a irrational number. Now next we have to prove that 1 by root 2 is irrational. So suppose 1 by root 2 is rational, then we have the form p by q. P and q are integers. Q is not equal to 0 and HCF of p and q it is 1. Then we are saying that root 2 will become equal to q by p. Now if we are writing 1 by root 2 is equal to p by q, so what we have from this is that p and q both these are not equal to 0. So it means we can write root 2 is equal to q by p, and this thing implies that root 2 is rational and this thing is not correct, that we have already proved that root 2 is irrational. So our assumption that 1 by root 2 is rational is incorrect. So we get that 1 by root 2 is an irrational number. Next we have to prove that 3 plus 5 root 2 is irrational. So suppose it is a rational number. So we will have some p and q which are co-prime and q is not equal to 0. P and q are integers. So we can write this number in the form of p by q. So what we get from this is it is 5 root 2 is equal to p by q minus 3. So this implies us root 2 is equal to p minus 3q over 5q. If we look at this numerator over here, this will be an integer. If p and q they are integers, then we are saying p minus 3q will be an integer and this will be an integer. It means what we get is this thing implies that root 2 is rational. You can write it in this form and this is not correct. Yes, we know that root 2 is irrational. It means our assumption that this number is rational is incorrect. So the given number 3 plus 5 root 2 is an irrational number. Next is root 2 plus root 3 is irrational. So suppose we are saying that this is a rational number. So similarly we will have some numbers a and b which are prime. We are talking about we have integers a and b which are co-prime, and b is not equal to 0, and we are saying that root 2 plus root 3 is equal to a by b. We are supposing this thing. Suppose that this number is a rational number, then root 2 by root plus root 3 is equal to a by b. So what we get is that root 3 is equal to a by b minus square root of 2. So when we square both these sides, we get 3 is equal to a by b square plus 2, it is root 2 square means 2 minus 2 times root 2 into a by b. So what we get from this is that 2 root 2 a by b is equal to a square by b square plus 2 minus 3. This is equal to a square by b square minus 1. So what we get from this is that root 2 into 2a by b, that is equal to a square minus b square upon b square. So we get root 2 is equal to a square minus b square over 2a b. Now if a and b are integers, then a square minus b square will be integer, 2ab will be integer. Both these values, these are integers, and the denominator will not be equal to 0. So what we see is, what this thing gives us is that root 2 is a rational number, and we know that this is incorrect. It means our supposition that this number root 2 plus root 3 is rational. What we are supposed over here, we assume that root 2 plus root 3 is rational. Our this supposition is wrong. It means that the given number is the irrational number. Now next we have to prove that square root p plus square root q is irrational, where p and q, these are the prime numbers. So again we suppose that square root p plus square root q is rational numbers. Then there exist co-prime numbers a and b such that square root p plus square root q is equal to a by b. Now we can adjust these terms, and we can write square root p is equal to a by b minus a square root of q, and when we square this equation, we get p is equal to a by b square plus square root of q square minus 2 times a by b into square root of q. So this thing gives us 2a by b times square root q, that is equal to a square by b square plus q minus p. So this gives us square root q is equal to a square b plus b cube into q minus p over 2 times a. As all these a, b, p, q, these are the, we are saying these are integers. So what we see is that this numerator is the integer, this denominator is the integer. So this thing implies us that root q, square root q, is rational number. The square root q is rational number, and this is incorrect because we know that if q is prime, then square root q is irrational. So we are saying this thing is incorrect. So the supposition we have made over here that square root p plus square root q is rational number is incorrect. It is not possible. Our supposition is wrong. So what we get is that square root p plus square root q is a irrational number.